This question is asking us to perform Lagrange Multiplier Method to solve a constrained optimization problem. We have an objective function, log x plus squared, natural log of x squared plus 1 plus natural log of y squared plus 1 plus natural log of z squared plus 1. And our constraint function is the sphere, x squared plus y squared plus z squared equals 12. So we're looking for points on the sphere that would end up giving us global maximum or global minimum values for our function. And so we start with the gradient of f. It's going to be 2x over x squared plus 1, 2y over y squared plus 1, 2z over z squared plus 1. Do the chain rule, 1 over the inside times the derivative of the inside. Now the g function is going to be the constraint set equal to 0. So x squared plus y squared plus z squared minus 12. The gradient on that is going to be just 2x, 2y, and 2z. Lagrange multiplier method says that the gradient on f must be equal to lambda times the gradient on g. And so this leads to 3 separate equations. On the one hand, 2x over x squared plus 1 should be 2x lambda. And same for y, same for z. Now we have to be careful. We can't just divide by 2x and cancel it out, because we could be dividing by 0 and that's not allowed. So what we'll do instead is we set it equal to 0 and we factor out. We'll have 2x over x squared plus 1 minus 2x lambda is equal to 0, and the same kinds of equations for y and z. So if 2x, let's factor out the 2x, and that would give us 2x times the quantity of 1 over x squared plus 1 minus lambda would be equal to 0. And similar equations for y and z. And so let's see. How do I shrink it? All right, that's fine. We'll have similar equations for y and z. Either x is 0 or lambda is 1 over x squared plus 1. The same is going to be true for the y and the z. Either y is 0 or lambda is 1 over y squared plus 1. Either z is 0 or lambda is 1 over z squared plus 1. And there's nothing to stop x from being equal to 0. Our constraint is x squared plus y squared plus z squared equals 12. It's okay for one of those to be 0 or 2 of those to be 0. It's not okay for all 3 of them to be 0. Let's take the case where one of them is 0 and the other 2 aren't. Let's take the case where 2 of them are 0 and the other one isn't. Let's do that on the next page. We got a little more room here. If x is equal to 0, let's take that into the constraint. X squared plus y squared plus z squared would be equal to 12. X is equal to 0, y squared plus z squared would be equal to 12. And let's say that's the only one that's equal to 0. Okay. So then we'd have lambda must be 1 over y squared plus 1, who also must be 1 over z squared plus 1. And so it tells us that basically y squared is equal to z squared. Not that y equals z, that's a possibility. Y is plus or minus z. But in the constraint, the squareds would be equal to each other, so it would be like having y squared plus y squared be equal to 12, or y squared being equal to 6. So we get two values, square root of 6 or negative square root of 6. And with those two values, there'll be two z values, square root of 6 or negative square root of 6. And we just arbitrarily chose x to be the one that gives us 0. It could have been y. Only one of them is 0. That's what we're looking at. And so, unfortunately, this gives us a whole lot of possible points. And so, let me write them. 0, root 6, root 6. 0, root 6, negative root 6. 0, negative root 6, root 6, 0, negative root 6, negative root 6. Whew. And we'd have another 4 of those making y being the 1, 0. And then another 4 of those making z being the 1, that's 0. Root 6, 0, root 6. Root 6, 0, negative root 6. Negative root 6, 0, root 6. Negative root 6, 0, negative root 6. Wow. Root 6, 0. Root 6, negative root 6, 0. Negative root 6, root 6, 0. And negative root 6, 0. These are all the possibility for one of them being equal to 0. What about two of them being equal to 0? Say that x equals y equals 0. And lambda then would be 1 over z squared plus 1. In the constraint, x squared plus y squared plus z squared equals 12. With these two zeroing out, that would make z plus or minus root 12. That's 2 root 3 or negative 2 root 3. And so that gives us 6 more points. 0, 0, 2 root 3, 0, 0, negative 2 root 3. Well, who's to say that x and y could have had to be 0? It could be x and z as 0. It could be y and z as 0. So many points coming out of Lagrange. So far, yeah, that's 18. Okay. It's impossible for them to all be 0 because the constraint would not be true. So we've handled all the 0 cases. Usually 0 is not a problem and usually doesn't give us any information, but here it turned out that it did, unfortunately. And so our next job then is to look at when none of them are 0. X, Y, and Z not 0. That means that the lambdas have to all be equal to each other. This is x squared over x squared plus 1, y squared plus 1, z squared plus 1, with nobody as 0. It basically says that they're opposites of each other. If we take them two at a time, it says that x squared is y squared, or y squared is z squared. Okay. That doesn't say that y is z. Y could be the opposite of z, and that could be true. we take that into the constraint, who was the sum of all of them squares being equal to 12. And if we go in terms of y squared, we can replace x by y squared. We could replace, x squared by y squared. We could replace z squared by y squared. And that would give us the fact that 3y squared would be equal to 12. Nicely, y squared is equal to 4. So y could be 2, or y could be minus 2. And then x would be plus or minus that. Z would be plus or minus that. And so that leads to 8 different points. If y is 2, z could be 2. And x could be 2. If y is 2, z could be negative 2 and x could be 2. If y is 2, z could be 2 and x be negative 2. If y is 2, then z could be negative 2 and at the same time x being negative 2. That's 4 points there, and 4 more points if y was negative 2. 2 and 2, negative 2 and 2, 2 and negative 2, negative 2, negative 2. All right. Wow. 8 points here, 6 points here, that's 14, and then 12 points there. What? 26 points coming out of Lagrange. That's insane. But that's okay. What we do with these points is we plug them into the constraint. We plug them into the function. Okay. And in the function, what we do is we square each of the inputs and add 1 to them, and take the and plug it into a log. It's the natural log of x squared plus 1, y squared plus 1, and natural log of z squared plus 1. Okay, so it's invariant about the plus or minus, and so let's take the most recent 8 points that we got. The x squared plus 1 is going to be 5, whether it's plus or minus 2. Same for the ln of y squared plus 1. Same for the ln of z squared plus 1. We're going to end up with, let's call these the c points. Our function at those is going to be ln 5 with 3 of those. 3 ln 5. Okay. Or the ln of 125. It might help us to actually write it out in terms of ln to see who's the largest. Usually Lagrange only gives you 2 values, but that's not going to be the case here. We got all these different types of points here. Let's call these 6 points here b points, with 2 of them 0. And with z squared is then 12, or so the constraint. Yeah, so then the function at the b points would be ln of 1, so that's going to be 0. And then we'd have the ln of 13 there. These guys are 0. This would be ln of 13 at each of those 6 points there. Yeah, at each of those 6 points we'd have ln 13. Okay. It'd be nice if it stopped there. Most Lagrange questions only have 2 outputs. But this Lagrange question has 3 different types of points, 26 points in total. And so at these A points, what's going on, where we have 1 0 and the other 2 not, z squared and y squared, they'll be equal to 6. And so these will be ln 7s. The function will be ln of 1 plus ln of 7 plus ln of 7. So that'll be the ln of 2 of those ln 7s. That'll be the ln of 49. Pull the power up. For every single one of those 12 points, that's going to happen. In our job, find extreme values. So the biggest is natural log of 125. That's our extreme max. That's our global maximum. The smallest would be ln of 13. That's our global minimum. And this other extraneous value here that came from our only one of them giving us 0. That's neither a global min nor a global max. Usually Lagrange doesn't do that. Lagrange is supposed to spit out only the global max or min, but here this is nothing. Neither global max nor global min. Sorry it took so long, but hopefully that was helpful. You have to consider all cases, and so we have to recognize when 0 is in the mix and how that affects it. Here we had some symmetry to help us out, and so we have finished the question. Thanks so much for watching. My name is Nakia. Remember, please like and subscribe. Comment down below. I'll see you in the next video. Wow.